All right, hey AP Chemistry. So I'm going to walk us through some more of our sample problems from our Unit 8 notes, Part 1. We already discussed sample problem 13 in class. We chose, it says, use the following information to answer the question. This data table shows, in no particular order, 4 acids that are chlorous, hydrochloric, lactic, and propanoic. And the only strong acid here is hydrochloric acid. Now, looking at this data, it says, for which acid is the value of the acid association constant Ka the smallest? Meaning the weakest acid and the largest pH. If I have a small Ka, it does not dissociate that much. I'm not going to get that much H+, so it's going to be a larger pH because it's going to be more basic. It's going to be more basic. Don't be fooled by that. And it's the weakest acid. So if I look at this data table, I'm just looking for the highest pHs. It's acid 1. That's why we chose that. And then in number 2, it says, which of the 4 acids listed in the table is hydrochloric acid? It's a strong acid. If you take the negative log of the concentration of HA, that's going to be equal to the negative log of the concentration of H+, which is equal to the pH. If I take the negative log of the concentration of the acid and I get pH directly, that must mean it's a strong acid. Also, I'll probably be looking for ones that have the lowest pH. So there's 2 things here, because it'll be my strongest acid. One in which I take the negative log and it gives me the pH directly from the concentration of the acid, and whichever has the lowest pH. Well, just looking over here, acid 2 has the lowest pH. So it's got to be my strongest acid. Acid 2 is definitely my strongest acid. And HCl is one of the strong acids. And if I take the negative log of 0.01, I'm going to get 2. If I take the negative log of 0.1, I'm going to get 1. If I take the negative log of 1, I get 0. So this is definitely, acid 2 is definitely hydrochloric acid because it's a strong acid. The negative log of the concentration directly equals pH. And then sample problem number 14 is a bit more, it's a multiple choice question from a previous exam, but it's a bit more applied. So it says HCHO2, this is formic acid, a weak acid, Ka is 2 times 10 to the minus 14th, dissociates in water, according to the equation above. Which of the following provides the best estimate of the pH of 0.5 molar HCHO2 and identifies the species at the highest concentration, excluding H2O? All right, so if this is a weak acid, right, and look at the Ka, it's a small Ka, or small value of K. If I have a small K, that's reactant favored. That means I have more reactants. Remember that from Unit 7. Unit 7, I have more reactants if I have a small Ka. So both of these will be in higher amounts. It's going to be mostly shifted to the left. And these are going to be in lower amounts. So the question says species at highest concentration. It's not going to be anything with H3O+, because they're going to be in lower amounts because it favors the reactant side. So I had to cross out A, and I got to cross out C. And now I'm left with B or D. So now I got to figure out what would be the pH of this weak acid. Now, if I were to take a guess, I'd probably go with the weaker of the pHs, which would be a pH of 2. But you could calculate this and solve this. Kind of a shortcut now. The Ka is going to be equal to x squared over 0.5 is equal to 2 times 10 to the minus 4th. How did I do all of that so quickly? Well, it's just from practice with doing ice tables. They all end up at the same. Look what I did. It all ends up the same. Basically, it just ends up with x squared over your initial concentration equals Ka. And then basically, it ends up being x is equal to the square root of your initial concentration of HA times your Ka. And this is a shortcut. If I want to solve for the value of x, I basically will take my initial concentration of HA, multiply it times Ka, and take the square root of that. So HA, initial concentration is 0.5 times 2, and I'm going to do this without a calculator because it's a multiple choice question. So 0.5 times 2 times 10 to the minus 4th is basically this 0.5 times 2 is half of that, 1.0 times 10 to the minus fourth. And if I take the square root of that, I'm going to get, you're taking the square root, you kind of like are halving the exponent. So the square root of that is actually going to be 1.0 times 10 to the minus second molar. And if I take the pH of this, it's equal to the exponent, 2. Negative log of 1.0 times 10 to the minus second is equal to 2. The correct answer is D. I did that all without a calculator, just to kind of give you a little trick with getting pHs. If I take the negative log of the concentration of H plus, usually the exponent is going to be equal to the pH. So if I had something times 10 to the minus third, probably the pH is going to be about 3. If I had, and you could look at on page 8, we're going to jump to page 8 and how they kind of match. Jump into page 8 when you were doing those or actually page 9, sorry, when you're doing those calculations, right? I have 1.0 times 10 to the minus third, pH is 3. I have 5.0 times 10 to the minus fourth. Let me plug that into the calculator. Negative log of 5.0 times 10 raised to the minus fourth, 3.3. Because it's like halfway, it's like almost 4, but it's actually a lot less than 4, right? But if it was 1.0 times 10 to the minus fourth, it would be about 4, right? Negative log of 1.0 times 10 raised to the minus fourth, it's going to be 4, okay? So approximately, the pH is going to be almost close to the exponent. So that's how I also knew to do that, okay? All right, now moving on to where we are going to be at, let's look at sample problem 15. This is big. This is from the 2018 free response question. And I had students kind of mess up on this a couple of years ago because they were thinking about it too much. So we have HF, weak acid. The ionization of HF in water is represented by the equation above. In a 0.035 molar HF solution, the percent ionization is 13%. Weak. Automatically, if it was strong, what would this be? 100%. So this is weak. Two particular representations of the ionization of HF molecules in the 0.035 molar HF solution are shown below in figure 1 and figure 2. Water molecules are not shown. Explain why the representation of the ionization of HF in figure 1 is more accurate than the representation in figure 2. The key below identifies the particle. So if you look at figure 1, it looks like I have HF remaining, 1 H plus that broke off. Sorry, 1 F minus. That's F minus, my bad. Key. I have 1 F minus that broke off, and I have 1 H3O plus that kind of broke off, and then the rest of them kind of stayed together. So if I had 1, 2, 3, 4, 5, 6, 7, if I had 8 particles, like 1/8 of them broke off or dissociated. And if I put that number into a calculator, 1 divided by 8 is actually about 0.13, which is 13% that dissociated. If I look at figure 2, this is 100% dissociation. Every F minus is available and every H3O plus is available. Cannot be figure 2. So why does figure 1 work? Because this is not 100% dissociation. This is 100% dissociation. So it cannot be figure 2 because figure 2 shows 100% dissociation. Also, 1/8 is about 13%, which is what it says it is in the top there. Done. Now it says B, use the percent ionization data above to calculate the value of Ka for HF. Now, my initial concentration of HF is 0.0350 molar. Now, if 13% of this dissociates, I'm going to be subtracting 13% of this, and that's how much H plus I'm making. So if I subtract 13% of 0.0350 molar, and I'm going to do this, 13 divided by 100, times 0.0350, that's actually my value of X. I'm going to subtract, this is how much is dissociating off. So I'm going to be left with 0.0350 minus 0.00455. I'm left with 0.030, I'm going to round that to 5 molar. And then my concentration of H plus is going to be equal to my concentration of F minus because of ice table. It's going to be 13% of 0.0350, which is 0.00455 molar. Okay? Actually, let me put this back to 3045. Doesn't matter. All right, now I basically have my equilibrium concentrations of everything because Ka is going to be equal to the concentration of H plus, concentration of F minus, all over the concentration of HF at equilibrium. So again, how did I do this very quickly? It says 13% of it dissociated. This is my value of X, right? If I did want to do an ice table, I'd have HF in equilibrium with H plus F minus, 0.03500, and then minus X plus X plus X, 0.0350 minus X, X and X, and I know that my value of X is equal to 13% of 0.0350. So once I got that number, which was 0.00455, I could plug that in for my value of X. And now I could plug those values in to get the Ka expression. So 0.00455, 0.00455, all over 0.03045. Plugging these in, I can get my value of Ka. 0.00455 times 0.00455 divided by 0.03045. And my Ka is 6.8 times 10 to the minus fourth. Definitely one of a weak acid. Oops, can't see that. All right, again, I'll say it again. How did I use the percent dissociation to figure out Ka? Well, percent dissociation tells me how much H plus is breaking off. And the moment I got how much H plus, I know how much F minus is going because it's a 1-to-1 mole ratio. Right? Another way of writing this equation is HF aqueous in equilibrium with F minus aqueous and H plus aqueous. Same thing. And if I know how much H plus breaks off, it's equal to the same amount of F minus because it's a 1-to-1 mole ratio. All right, and then the last question says, if 50 milliliters of distilled water is added to 50 milliliters of 0.0350 molar HF, will the percent ionization of HF in the solution increase, decrease, or remain the same? Justify your answer with an explanation or calculation. Well, if I add it, I'm diluting the amount of HF. I'm going to leave this open here because of the timing of this video. In a future video, I'm going to leave C up to you. What affects equilibrium concentrations? What affects how much H plus is going to be produced in solution? If I add water, what's going to happen to my equilibrium concentration? Is water going to change how much H plus breaks off in solution? I'm going to leave that as a question for us for a future video on percent ionization. So my next video is going to be talking about the last page of these notes, percent ionization.